Hello, I'm Tyson Lauby. Today I'm going to be presenting on the OIOT WSM anodizing power condition. The WSM tackles anodizing process limitations that are often treated in the industry as chemistry problems. And while chemistry matters, the largest problems exist in the form of the electrical energy itself. The WSM addresses this by altering the power entering the anodizing interface, changing the capabilities for thicker coatings, faster throughput, improved quality, and higher profits from existing infrastructure. For a line owner, the fastest return is certainly not building a second line. A second line means more tanks, hoists, chillers, rectifiers, ventilation, permitting, installation, and on and on. This can easily become a 6 or 7 figure project. The preferred solution is increased efficiency. With the example of a 12,000 amp line, the WSM is retrofitted into the existing rectifier to tank path. Instead of duplicating the line, the facility simply adds a power conditioning system. If the installation can now process twice the product in the same amount of time, the ROI is simple. Spend like a minor upgrade, but capture full line expansion value. Same line, greater throughput. For anyone not familiar with anodizing, it is a controlled process where electricity is used to grow a ceramic oxide layer on a cast or machined aluminum part. This oxide layer is not a paint sitting on the surface. It is a porous crystalline structure that is integral to the material itself. Anodizing improves corrosion and wear resistance, hardness, paint adhesion, and can even be a colorful decorative finish. Anodizing is critical to aerospace, defense, automotive, architecture, and industrial applications, and is a production process tied directly to modern high-value manufacturing. Conventional anodizing works, but it has limitations. As the coating thickness increases, so do voltage, heat, and electrical stresses. These compound the likelihood of burning, discoloration, or inconsistent oxide coating. To manage this, facilities run slower, cool harder, use chemical additives, or stay inside conservative process windows. These choices protect quality, but they reduce throughput and increase cost. Our research and testing back thesis is that the anodizing process is being constrained by how the energy is delivered into the electrolyte, oxide, and aluminum itself. We are not asking facilities to tear out their line, replace their rectifier, abandon their chemistry, or rebuild the plant. Our offering is a retrofit-compatible device that can be placed into an existing production environment. This matters because it creates an easier pilot path. A facility can test the system on real parts, compare coating performance, and evaluate the economics without treating the project like a plant replacement. Practical deployment is our wedge. Recognized literature identifies AC superimposition on DC as a known approach. That literature illustrates the method to lower anodic voltage, less heating, reduced burning risk, and is useful for difficult alloys. But it also identifies the barrier. Historically, the required equipment was complex and expensive. The science was sound, but the equipment impractical, making it unattractive. That is the gap that the WSM addresses. We are not claiming to have invented AC on DC anodizing, but we are claiming to have made the physics industrially deployable. The WSM changes the role of the power source and adds functions that even the early developers of this technology never thought possible. Frequency, amplitude, waveform shape, voltage and current phasing all become process variables. We are not simply adding a little AC to DC. We are giving the end users ultimate control over their process variables. And when a process variable becomes controllable, the process itself can be optimized. This is the disruption, turning power delivery into an active anodizing process control. The obvious question is this: if anodizing has roots going back decades, why has the industry not adopted superimposed AC on DC power? And the answer is simple: a technology fork. Chemical additives became one path for improving performance, and new switch mode rectifiers became another. As DC plus AC systems were bulky, costly, and limited by the power electronics of their time, they were not adopted. The industry simply made a cost-value decision and optimized around switch mode rectification, cooling, and chemistry. The path was taken, and AC superimposed DC was discarded and forgotten. In initial testing, using standard sulfuric acid, moderate temperature, and no specialty additives, we observed a meaningful movement in the process window. Difficult alloys such as 2024 and A380 resulted in coatings up to 4 times thicker. Standard alloys, including 6063 and 7075, were successfully run at up to triple the threshold of established safe maximum current density limits. Testing also showed decreased voltage buildup compared with standard rectification behavior, in some cases dropping energy input by up to 25 volts. This is a very significant decrease in energy consumption. Of course, these are initial results, not the end of validation, and not maximally optimized. However, these strong indicators of performance justify continued development, independent revalidation, and pilot testing. For the line owner, this impact goes beyond throughput. More coating per unit time is the headline, but the broader value is a larger operating envelope. They can reduce heat and chiller burden, have less dependence on specialty additives, lower their energy costs, and meet difficult specifications for hardness, thickness, and alloy performance. This technology is disruptive in the best sense of the term, as it does not ask the industry to throw away what already works. It instead helps the industry get more from what it already owns. OIOT is now focused on turning early evidence into industrial adoption. We currently have a revision 4 prototype in development. We are working with a Midwest switch mode rectifier company, and we have advisory support connected to prior research in this field. Our goal is not to replace the anodizing industry. Our goal is to modernize the systems that drive it. Same lines, more value. And I'm happy to take any questions.
Thank you.